Hi, in this video we are going to talk about maximum heaps. So we have been discussing that for a maximum heap, the greatest item is in the root node, and it is true for every single subtree, like this for example, or this, that the parent is greater than its children. As you can see, 19 is greater than 17 or 3, 36 is greater than 25 or 1. It's very important that basically the order doesn't matter as far as the left and the right children are concerned. As you can see here, for this subtree, the left child 17 is greater than the right child 3, but here, for example, for this subtree, the left child 2 is smaller than the right child 7. So it doesn't matter, it's not like binary search trees that the left child has to be smaller than the parent and the right child has to be greater. So basically, for a binary search tree, the right child is always greater than the left child. For heaps, this is not true. As you can see, 17 is greater than 3, but 2 is not greater than 7. It doesn't matter. What's important that the parents are greater than the children. It's very important that somehow we have to represent this tree-like structure, and we are able to construct a one-dimensional array, so that's why we have assigned indices to every single node in the tree-like structure. And we usually assign 0 to the root node, then 1 for the left child, 2 for the right child, and so on. 0, 1, 2, 3, 4, 5, 6, 7, 8 in a sequential order, because heaps have to be complete. That's why we are able to assign the array indices from left to right on a line-by-line basis. And then we just have to construct this array, and the 0 index is going to be the 100. The left child is going to be the 19 with index 1. Then 36 is the right child with index 2, and so on. So basically we assign indices to every node in the heap, and the index will be the index in the one-dimensional array. This is how we represent the tree-like structure with the half of a one-dimensional array. And this is why I said that heaps can be considered as an abstract data type, because basically we have the heap and we have the underlying representation as a one-dimensional array. And a one-dimensional array is a data structure. Anyways, it's not that important, but it's good to see that heaps are usually called a data structure, but basically it can be interpreted as an abstract data type because the underlying data structure is a one-dimensional array. It's very important that we are able to construct some patterns, some rules, that if we have the parent node with the index I, then the left child is going to be the 2 times I plus 1. This is how we are able to look up the left child in the one-dimensional array. The right child is the 2 times I plus 2. This is how we are able to find the right child for a given node in the one-dimensional array. Let's consider, for example, 17. 17 has the index 3. Okay, we have the 17 here. How are we able to find the left child in the array? The left child is going to be 2 times I plus 1. So 2 times 3 plus 1. So basically 7. Yeah, here's the 2 with the index 7. What about the right child? It is 2 times I plus 2. 2 times 3 plus 2, so 6 plus 2, so 8. We just have to look up in the array where the index is 8. It is the 7. So this is how we know that the 17 will have the left child 2 and the right child 7. And it's very important that the root node is always the array with the 0 index. For a maximum heap, it's going to be the largest item. For a minimum heap, it's going to be the smallest item. What about building a heap? For building the heap, first we insert the data to the heap and we check whether the heap properties are met or they have been violated. If the heap properties are violated, then we reconstruct the heap in order to make it a valid heap. This is called the heapify process. So for example, we insert 23. It's going to be the first item in the one-dimensional array and it's going to be the root node of the tree-like structure. Then 5 is going to be the left child of the 23, no matter that it's greater or smaller than the root node, because this is how heaps are constructed. It has to be complete, so we inserted to the index 1 in the one-dimensional array, and we have to check that whether it's going to be a valid max heap. It's going to be a valid max heap because the parent is greater than its children. Then we insert 100. It's going to be the right child of the root node, so the index 2. As you can see, basically when we construct a heap, we are just going to insert the items on a one-by-one basis into the array. Okay, so 100 is going to be the right child of 23, but it is a maximum heap, so basically we violate the heap properties. Because for a maximum heap, the greatest item is in the root node, so we have to swap them. After the swap operation, it's going to be a valid heap. Then we insert 2. It's going to be inserted to be the left child of 5 because this is how we construct a heap. This is how we insert items. We insert in order to make sure that the tree-like structure is going to be complete. Then we check whether we have violated the given heap properties. We haven't violated the heap properties because the parents are greater than the children. We have the 100 as a parent, it's greater than 5 or 23. We have another parent, the 5. It's greater than 2, so it is a valid heap. Then we insert 210. It's going to be the right child of 5 because when we construct a heap and when we insert an item, we have to make sure that the tree-like structure is complete. So we are not able to insert the 210 here or here. We have to insert it to be the right child of 5. But it's very important that it is not a heap, because in a heap, for a maximum heap, the greatest item is in the root node. So we have to heapify. We have to swap these and we have to swap those two in order to make sure that in this situation it is a valid heap. We have the parent 210. It's greater than 123. We have another parent, 100. It's greater than 2 or 5. So it is a valid heap. And again, the parent node, if we have the parent index I, then the left child is going to have the index 2 times I plus 1 and the right child 2 times I plus 2. It's important when we are dealing with the array representation of the given heap. This is how we are able to find the parent, for example. We have a right child, then we are able to find the parent for that given right child. For heap sort, it's going to be essential. So for example, 210 with the 0 index, the left child is going to be the index 1 and the right child is going to be the index 2. Okay, this is exactly what we are after. What about the 100? It has the index 1, so the left child will have the index 3, the right child will have the index 4, so 2 and 5. Yeah, this is exactly what we are looking for. So this is how we are able to manipulate the heap tree-like structure via a one-dimensional array of integers, for example. And let's take a look at the running times. It takes ordo n, so linear time complexity, to construct a heap. Why? Okay, maybe we have to reconstruct the array if the heap properties are violated, but it takes ordo log n, so logarithmic time complexity, because we just have to, for example, as you may recall, when the 210 were here, we just have to swap it with the parent, then swap it with the parent. So basically we don't have to bother about half of the tree, so that's why it will have a logarithmic running time. So ordo n plus logarithmic time complexity is equal to ordo n linear time complexity. Inserting an item to the heap is just adding the data to the array with incremented index. So we just have to insert the data into a one-dimensional array. Then we have to heapify. We have to make sure that the parents are going to be greater than the children for a maximum heap. If we are building a minimum heap, then of course the parents has to be smaller than its children. Okay, that's all about the basics. Thanks for watching.